Nuclear chemistry kinetics, a fascinating field that studies how fast and by what mechanisms nuclear reactions occur. Nuclear chemistry kinetics examines the rates and mechanisms of nuclear reactions. It covers radioactive decay, where unstable nuclei transform and release radiation, modeled by the first equation shown. In nuclear fission, heavy nuclei like uranium split, releasing significant energy as per shown in the second equation. And lastly, nuclear fusion combines like nuclei such as hydrogen to form helium, releasing energy as shown in the last equation. Kinetics play a vital role in nuclear reactions. First, understanding radioactive decay is essential for applications like radiometric dating, medical imaging, and managing nuclear waste. Next, advancing nuclear fusion depends on kinetic studies to achieve the high temperatures and pressures needed for sustained reaction. Finally, in nuclear fission, kinetics ensures control over chain reactions, promoting safe and efficient energy production. Overall, kinetic studies are crucial for both the development and safety of nuclear technology.
Discuss the concept of rate law. In nuclear reaction like radioactive decay, the rate law shows how fast a radioactive substance breaks down. This depends only on the material's amount, not external factors like temperature or pressure. For a radioactive decay, the rate is always first order. This means the rate of decay is directly proportional to the number of undecayed nuclei. The formula is shown below, where lambda is the decay constant and the symbol of n is the number of undecayed nuclei. Lastly, the half-life is the time it takes for the half of the substance to decay. For example, carbon-14. It has a half-life of 5,700. Let's look at the decay of carbon-14, which is an example of radioactive decay. Step 1. It shows how we calculate the decay constant using the relationship of lambda equal to ln2 over T1 over 2. In step 2, we calculate the remaining of carbon-14 after a given time using the formula. For example, after one half-life of 5,730 years, the remaining amount is 50 grams from an initial 100 grams. Finally, the graph shows the exponential decay curve of carbon-14. Notice how the red dashed line marks the half-life of 5,730 years, and the green dashed line shows the remaining of 50 grams after one half-life. The curve reflects how the amount decreased by the half of the regular.
An elementary reaction is a single-step reaction with a single transition state and no intermediates. These reactions are the simplest form of chemical reactions and cannot be broken down into simpler steps. One example of radioactive decay is alpha decay, where the nucleus emits an alpha particle. This reduces the number atomic by 2 and mass number by 4. For instance, uranium-238 undergoes alpha decay to form thorium-234 plus an alpha particle. Molecularity refers to the number of reactant species such as atom, ion, or molecule involved in an elementary reaction. There are three types of molecularity, which is unimolecular, bimolecular, and thermomolecular. Main to discuss is unimolecular that involve a single reactant species such as the radioactive decay.
Nuclear chemistry, understanding how and why nuclear reaction occur requires exploring several key reaction theories. Two of the main theories are collision theory and transition state theory. The collision theory, it explains the nuclear fission and fusion, in which this phenomena happens when the kinetic energy are enough, the particle orientation is correct, and more frequency of the particle colliding. While the transition state theory explains the alpha and beta decay, in which when the particles excite and become the activated complex by surpassing the activation energy. These unstable particles can be the product of the reaction or reverted to its stable reaction mechanism. Describe the step-by-step sequence of elementary reactions by which a nuclear reaction occurs. In nuclear chemistry, mechanisms are often more complex than in chemical reactions, involving multiple steps and intermediate particles. The two of the mechanisms are direct reaction and compound nucleus reaction, which both have a different kind of mechanism concept.
The following are some key applications of radioactive materials. Firstly, safety and environmental applications. Secondly, radiocarbon dating. And lastly, medical imaging. However, the use of radioactive materials also brings certain implications such as ethical concerns, understanding Earth history, and lastly, scientific limitations.